Delay robust nonlinear control of bounded input telerobotic systems with synchronization enhancement. In this work, we have studied teleoperation systems that are subject to bounded actuation and time-varying delays in the communication channels. In practice, the amplitude of control signals is capped by the torques that the actuators can supply. In other words, they are subject to saturation. This limitation and also time delays should be taken into account in the controller design, otherwise it may render unintended responses and even the system's instability. Robustness to larger time delays comes prevalently at the cost of increased settling time for position synchronization. In this work, given time-varying delays and bounded actuation, we propose a controller that not only mitigates the trade-off between the settling time of the synchronization and magnitude of the time delays, but also exhibits better transient error in position convergence. We have used Lagrangian systems for modeling manipulators in the system. Also, Lyapunov stability theory is utilized for stability analysis. For validation of theoretical findings, we have done simulations and experiments. Here you see the schematic of a bilateral teleoperation system. A bilateral teleoperation system is comprised of four main elements, namely leader robot, follower robot, communication channel, and controllers. The controlled coupling between robots makes the follower robot to be under the control of an operator who manipulates the leader robot. Specifications that usually are studied in these systems are stability of the system, performance including tracking in joint space or task space, and force reflection or generally transparency, which measures the quality of teleoperating and how good the force reflection provides the operator with a sense of manipulating the object directly. This work studies bilateral teleoperation system in the joint space, given that the manipulator's motions are modeled by Euler-Lagrange equation. M sub k is inertial matrix, C sub k is Coriolis centrifugal matrix, G sub k is the gravitational vector, tau sub ek is the exerted torque, S sub k of tau sub k is the control input subjected to saturation, Q sub k denotes the joint positions, Q dot sub k denotes joints velocities, and Q double dot sub k denotes joints acceleration. The saturation of the control signals is modeled by saturation function, where B sub ki is the saturation level of ICE actuator and tau sub ki is the controller of ICE actuator. Note that the subscript k shows leader and follower robot. Some assumptions are considered. The saturation level of each actuator is larger than the upper bound of the relevant element of the gravitational vector. Here, omega sub ki is the upper bound of ICE element of the gravitational vector. The first assumption implies that each actuator can overcome its corresponding gravity. Second, time-varying delays are assumed to be continuous in time. Also, we have a definition that says the operator and environment are passive if there exists positive constants such that the relation you see satisfies. Joint positions errors are defined in two sides, namely leader side and follower side. Since the system is a bilateral teleoperation, signals are mutually exchanged between two robots. In the leader side, the error is the difference between joint positions of the leader and delayed positions of the follower that are transmitted to the leader side. D sub S is time-varying delay in the follower to leader communication channel. In follower side, the error is the difference between the joint positions of the follower and the delayed positions of the leader that are transmitted to the follower side. D sub M is time-varying delay in the leader to follower communication channel. Also, EM0 and ES0 errors are defined for ideal conditions, meaning having zero delay. Here is the proposed nonlinear controller where sigma 1 and sigma 2 are positive real numbers. Capital P is a nonlinear function that have some properties and will be mentioned next. G sub k is for gravity compensation. Also, for simplicity and later usage, the first three terms in the controller is defined as delta sub k. If we define small p sub I as the elements of the nonlinear vector function capital P, they are required to have some properties. They are cyclically increasing, they are continuous, they are passing through the origin, they are concave for positive arguments and convex for negative arguments, they are odd functions, and they have continuous first derivative around the origin. Also, Ni is defined as the supreme of scalar nonlinear function p sub I related to the joint I. For instance, the arctangent is a nonlinear function that embodies all the mentioned properties in the previous slide. You see the function in two cases. First, a sub I is bigger than 0 and it is less than or equal to 1. And second, a sub I is larger than 1. Here I bring up two lemmas that are utilized in the stability analysis. Please note that d bar sub s is maximum of time varying delay in the follower to leader communication channel, and also d bar sub m is maximum of time varying delay in the leader to follower communication channel. Let x sub t be the state of the system where it is equal to x of t plus zeta, and x of t is comprised of joint positions and velocities. Zeta is between minus d max and 0, where d max is the maximum time delay across the communication channels. For stability analysis, we come up with a Lyapunov-based functional where it is the summation of v1, v2, v3, v4, and v5, where v1 is in a quadratic form, so it is positive. v2 is positive because of passivity definition. v3 is positive if the absolute value of delta sub ki is less than b sub ki. Also, v4 and v5 are positive since the vector function p is an odd function. Here it is shown why v3 is positive. Under the condition was given for v3 in the previous slide, delta sub ki would be in the linear part of saturation function, so we will have two cases, and jointly it can be shown as. Note that sigma 2 needs to be positive, and we choose it much less than 1 to leave more room for error signal to have better synchronization performance. The time derivative of Lyapunov functions would be respectively as, and therefore v dot would be the summation of these terms. Finally, the time derivative of v can be simplified to the relation you see, so for having v dot less than or equal to 0, we need to have sigma 1 larger than 2 times tr, where tr is the maximum round-trip delay defined as the guy you see. Thus we have three conditions, where the first one is equivalent to the relation is mentioned for ni. v dot less than or equal to 0 implies that all terms in v of xt are bounded, so error signals and joint velocities are bounded. By substituting them into the closed-loop dynamics, and given that these underlying terms are bounded, we can conclude that the acceleration of joints are also bounded. Given that the derivative of the function p is bounded, we can conclude that these guys are bounded. Consider again the final relation we found for v dot. By defining psi and integrating both sides of this relation from 0 to t, and regarding the figure you see, we would have three cases, which implies that q dot k or p of q dot k is member of L2 space, or the L2 norm of those time functions are bounded. Previously, we knew that the joint accelerations and the derivative of p of q dot are bounded, so using Barbalat's lemma, q dot k or p of q dot k converges to 0, which has only one meaning, that his q dot k converges to 0, since the nonlinear function p passes through the origin. We showed that the joint velocities converge to 0. In a similar way, we can show that joint accelerations converge to 0 as well, which I spare you the details. Considering the closed-loop dynamics in free motion and noting that these underlying terms converge to 0, and knowing that delta sub ki is in the linear part of saturation function, and delta sub k becomes g sub k minus p of ek, then we have, and so, which implies that p of ek or e sub k converges to 0. Now consider the case that the operator exerts a non-passive force and the environment is passive. Let x sub k be the position vector of robots end effectors. We know that the end effector velocity is equal to j sub k multiplied by joint velocities, where j sub k is the Jacobian matrix. Let f sub em and f sub es be the operator and the environment's applied forces respectively, where r sub m is a positive bounded vector and alpha m and alpha s are bounded non-negative constants. These forces will be substituted into the closed-loop dynamics. For stability analysis, we come up with similar Lyapunov functionals you see as v1, v2, v3, and v4. Finally, the time derivative of summation of all Lyapunov functionals can be simplified as the relation you see, in which sigma 1 being bigger than or equal to 2 times tr is a sufficient condition for having this highlighted relation. If this is satisfied, we will have all terms in v of x sub t bounded, meaning that error signals and joint velocities are bounded. Consider the situation that the underlying relation is not satisfied, meaning that we have. Now again, consider the applied forces I introduced in the previous slides. Since in practice the operator can apply a bounded force, then f sub em and rm are bounded, and consequently x dot m would be bounded, using which one can conclude that x dot sub k is bounded. Since x.k and Jacobian metrics are bounded, then joint velocities would be bounded. In a similar way, we can show that the joint accelerations and errors also would be bounded. For a study of forced reflection, suppose that the end effector of the follower robot is in a hard contact with the environment, which implies that the joint velocities and accelerations are in a quasi-static situation. Substituting this into the closed-loop dynamics, we can see that the exerted torques can be bounded and according to the nonlinear function P of Ek. Since P is an odd function, then the summation of applied torques would be approximately equal to 0, which implies that the force the environment applies on the end effector of the follower has a relation with the operator's applied force, where this guy is the pseudo-inverse of Jm transpose. Since tau Ek is bounded by the nonlinear function P, then the reflected force can be concluded that is also bounded. For simulations, the leader and follower robots are considered to be 3 degrees of freedom planar robots. The first table shows the physical parameters of the robots. The second one shows the saturation levels of the actuators for each of the manipulators. The third table shows time-varying delays and the maximum time delays. And also the last table shows the controllers. To simulate the forced reflection, we assume that in the follower side there is a wall at positive x direction and at x equal to 0.65 meter. We suppose that the wall behaves like a spring damper such that if the end effector of the follower robot exceeds 0.65 in positive direction, then the wall will exert a force in negative direction and equal to the relation shown for f sub wx. Also, we assume that the wall doesn't apply a force in y direction. The simulation results are provided. The first figure shows the force the operator applies in x direction on the end effector of the leader robot. Figure 2 shows the operator and wall's applied torques and also shows the joint positions of the robots. As you can see in the second figure, in steady state, the reflected torque from the wall tracks the applied torque by the operator. Also in free motion, the joint positions converge. In these results, again the first figure shows the force the operator applies in x direction on the end effector of the leader robot. Figure 2 shows the joint positions errors in free motion for the proposed controller and the benchmark controller. As you can see, the proposed controller outperforms the benchmark controller. Here you see the setup utilized for experiments. We have experimented the proposed controller on a bilateral teleoperation system comprised of a phantom premium robot as the leader and the Kwanzaa robot as the follower. The first joint of the phantom robot is fixed to make it a 2 degrees of freedom robot. We utilize this system for performing a peg-in-hole task. These results show XY position of the follower robot's end effector and the environment's force exerted on the robot's end effector, both in the peg-in-hole task that contains both free motion and contact motion. So, this figure shows the joint positions of the robots in the peg-in-hole task. As you can see, in free motion, the follower robot's joints track the leader's robot. Also, in contact motion, we have a bounded position error. All these are in line with the theoretical findings. Thank you so much for your attention.